Well, welcome back. In this lesson we are going to work on doing some proofs using our coordinate geometry, and we're going to go ahead and use those the coordinate geometry to do our proofs to prove some of the theorems that we've been working with, and we're going to prove those using our coordinates. So the very first problem here in writing a coordinate proof, it says to use coordinate geometry to prove that the midpoint of the hypotenuse of a right triangle is equidistant from the three vertices. So we're going to be given that we have a right triangle, and in this drawing they have the triangle labeled as triangle OEF, where angle O is the right angle, and we're given that M is the midpoint of segment EF. What we need to prove is that M is the same distance from point E and point F and point O. So we need to prove that those lengths are the same lengths using our distance formula. So here we go. By the midpoint formula, we first of all need the coordinates of M, which is the midpoint, and M's coordinates, if we use the midpoint formula, we will get A comma B for the midpoint formula. And the way we're going to do that, we would just take each of the coordinates of E and F, add them together and divide by 2, so you'd have 2A plus 0 over 2, 2b plus 0 over 2, and then if we divide each of those by 2 we get a comma b. So those are the coordinates of the midpoint. And then we need to use the distance formula to find how far it is from O to M, E to M, and F to M. So one at a time, here we go. O to M, remember this has coordinates a comma b, so it's going to be a minus 0 squared plus b minus 0 squared, the square root, so it's just a squared plus b squared. To get the distance from F to M, right here, from F to M, remember this has coordinates A, B again, so we'd get 2A minus A, the quantity squared, plus 0 minus B, the quantity squared, so that gives us A squared plus B squared when we simplify. And then for E to M, we get 0 minus A, the quantity squared, and 2B minus B, the quantity squared, which gives us A squared plus B squared again. So you can see that all three of these we did get the same length, and since they are all the same length, the midpoint of the hypotenuse is equidistant from the vertices of the right triangle. So that was what we were trying to prove. Here's a second problem. It says write a coordinate proof of the trapezoid midsegment theorem. And the trapezoid midsegment theorem says that if we have a midsegment MN, then we need to prove that the midsegment is parallel to both bases and its length is half the sum of the other two. So first of all, let's go ahead and use the midpoint formula to find the coordinates of M and N. And when we do that, we get M is equal to B comma C and N is equal to A plus D comma C. So again, to find those midpoints, you're just using point O and R and point P and A and finding the midpoint of those two sides. Then we're going to use the slope formula to show that MN is parallel to both bases. So the slope of MN, okay, the slope of MN using the coordinates that we obtained up here, okay, we would get C minus C over B minus A plus D. So we end up with a slope of 0 for MN. And you can see likewise if we go through and find the slope of RA and OP, the slope of this segment and the slope of this segment also work out to be 0. So they are all parallel. So we've proven this part of the proof. We've proven they're all parallel. On the next slide, we'll prove the last part where MN is half the sum of the length of the two bases. So this is where we're going to prove using the distance formula that MN is equal to the sum of RA plus OP divided by 2. So I went ahead and wrote in the coordinates of vertices M and N for you in here from the last slide. And then these are the distance formulas. We've been through this a lot of times, so I'm just going to kind of buzz through this kind of quickly. And you can pause this and take your time and actually go through all of the math here. Segment MN's distance, the length of that segment, will be the difference in the y-coordinates squared plus the difference in the x-coordinates squared. And when we simplify that, we get A plus D minus B. For OP, we get 2A, and for RA, we get 2D minus 2B. So now we need to just plug those all in to the formula. We need to check that the length of MN is half of the length of the sum of the other two. So we're going to go ahead and substitute those in. So what do we get for MN was A plus D minus B. We just substituted this in the top here. I'll go ahead and circle this so you can see where this came from. We substituted that for MN right there. And then this is OP. And that's going to get substituted right here. And you can see that right there. And then lastly, 2D minus 2B is the length of RA on the right hand side, and we've substituted that there. Okay, so when we add all these three together and divide by 2, we get A plus D minus B, and that is exactly what the length MN was. And that was the last thing we needed to prove. So we proved that the mid-segment is parallel to its bases, and its length did work out to be half the sum of the other two bases. Alright, on this last page it says write a coordinate proof of the triangle midsegment theorem. That will be very, very similar to the last two slides using the trapezoid midsegment theorem. So I've got it set up for you. You need to fill in the given and what you need to prove, and go ahead and work on that and bring your answer to this one to class. See you next time.